So welcome everybody. We have a great pleasure of welcoming Professor Govindarasu Manimaran, who is coming from Iowa State University and will be talking about cyber physical system security for smart grids. This is our Friday computer science seminar sponsored by VCU Cybersecurity Center. Very briefly, mark your calendars for another talk sponsored by CCI, Main Hub, John Doyle's talk next Thursday. And as a quick reminder, Cybersecurity Center sponsored events are recorded and posted on our VCU Cybersecurity website. So without further ado, thank you very much for joining us, Manimaran, and the podium is yours.
Yeah, thank you so much. Could you please enable the screen share?
Yes. You should be good to go now.
Okay. Can you see my screen now?
Yes, perfect.
Okay.
Thank you.
Yeah. Thank you very much. Really appreciate Vilas for inviting me to give this seminar. Really, I appreciate. I look forward to the opportunity to interact with you all. It's a great opportunity to sort of disseminate knowledge, not just the community that you are familiar with, but also broadly to like computer science, those kind of community. It's very important. As Professor Miller's mentioned, I work at Iowa State University. I've been doing research in CPS security for more than a decade now. Prior to that, I used to work in internet security. I know quite a bit of things in computer engineering. That used to be my home even now. But most of my work recent years have been on cyber physical system security. So I'm going to highlight some aspect of research that we have done last several years to give an idea what this kind of research. And it's, as you know, many of you have been working on this research, but there are a lot of things one can still, or the community as a whole needs to do in terms of R&D, collaboration, and so on. So going forward, so the title is the title of the talk is CPS security for the smart grid. So I'm going to go through several slides just to give the context and the broad overview about cybersecurity in this context, then some case studies. Then towards the end, I will talk about cybersecurity testbed. So as you all know, the modern grid, smart grid we call it, is no more just a physical system. It is a cyber physical system from a NIST framework document. This was very well articulated. As you see, there are physical assets in the power system, transmission, generation, distribution, and so on. Those physical assets are monitored and controlled through sensors, communication networks, computational analytics, decision-making, logic, all kinds of things. There is a lot of cyber, sensing, control, communication. They all collectively form the cyber layer. They are superimposed on the physical layer for efficiency, reliability, and performance of the grid itself. While these things are great, but introduction of more cyber components also introduces risk to the infrastructure. They are susceptible to attacks and so on. So we need to worry about cyber security, and also the adversary. I will show a slide. They are becoming more and more sophisticated and advanced. So this is a typical communication type of network architecture view, wherein you see control center. There is a local area network, a lot of servers and analytics that's happening. Then there are hundreds of substations that come under one control center coordination and control territory. Each substation has its own local area network, a lot of PLCs, intelligence electronic devices, relays, phasor measurement units, all kinds of devices, data concentrators, those things, machine-to-machine communication, those things happen. These substations, they communicate via wide area communication. Sometimes they are dedicated lines, sometimes they are relying on public internet through VPN and other forms to connect to the control center. Then you see a corporate network on the top. Those corporate network or market servers and other things, they may interact. They have connectivity to the control center. And also from remote maintenance perspective, engineers from different locations, they can connect to the substation for monitoring and configuration management, all kinds of different things. Of course, all those connections, whether they are permissible or not, again, it depends on the organization and utility. But the idea here is there is so much connectivity, there are so much geographically distributed infrastructure, there is so much legacy infrastructure. That means old devices and communication protocols. So how do we go about securing them while we are trying to modernize the grid with the new sensor, new capabilities, new analytics? We need to also make sure how do we retrofit cybersecurity into the existing old grid. So it's a twin challenge. That means the adversaries are growing, the sort of attack surface keeps growing, but at the same time we need to make sure how do we secure legacy infrastructure. So from the point of cyber threats, many of you very familiar with it, targeting critical infrastructures, whether it's a grid or other critical infrastructure like transportation and so on. There are various forms of attacks. This is not exhaustive classification, but just to give an idea, could be protocol-based, social engineering, intrusions of different kind, malware, very common thing that have happened recent years, targeting critical infrastructures, DOS attacks and denial of service attacks, and so insider threats and so on. So the idea here is how do we sort of protect the infrastructure against these threats, and also how do we detect, how do we mitigate this kind of defense in depth kind of solution that are needed. Before getting into the solutions, I want to give you a general outline. The cyber threat landscape is dynamic, it's not fixed. What you see here is the threat landscape. This was a report published by DOE and NERC jointly. This is called high impact, low frequency events, like solar flare, this kind of things, or GMD, geomagnetic disturbance of some kind. Those are all very high impact events, but less likely. In that context, they also identified cybersecurity by an advanced persistent threat like state actors targeting critical infrastructure, less likely, but highly impactful. That's what you see here. Strategic information warfare, highly structured, but very less likely. Likelihood is very less, but the consequence will be very, very high. So what this kind of map provides, what is the risk to the infrastructure, the likelihood times the consequence. So one has to look at, there are some events like probing, very common thing, but the consequence is very little. We don't need to worry about, but a lot of things that goes into the red zone, those are high risk scenarios. They need to be taken care, that could come from the state actors or could be from more advanced adversaries targeting the infrastructure for whatever be the reason. So the idea here is this map, it's a little bit old document, but it keeps changing. This is not fixed or it's not static, but it kind of gives you this kind of idea. This adversaries, they keep attempting, they become more and more advanced, and they have more capabilities. So the cyber threat landscape is dynamic. So from the attack surface point of view, as I mentioned, there is connectivity to the internet or public network, to the corporate server, or even to the substation directly for remote monitoring and so on. So you have a substation, wide area communication, control center in turn having connectivity to the corporate network. All these things, there are different attack paths. Attackers sitting in somewhere in the internet, they can gain access into one of these infrastructure element from there, like have a foothold from there, getting access into the next level, and causing major impactful events. It's quite possible. It has happened multiple times. But the idea here is how do we systematically analyze the attack surface? Attack surface is increasing. How do we systematically analyze? How do we mitigate any risk associated with those attack surface? So attack surface analysis and also attack reduction, the probability of those attacks happening, that has to be reduced. The challenge here is, unlike internet, those kind of environment, this communication pattern within the OT, operation network or control system, pretty static. There is no dynamism involved. It is easy for the adversary to infer what's going on, and they can create stealthy attack. On top of that, these are legacy infrastructure. They don't have state-of-the-art cybersecurity solutions. And the new trend, as I mentioned, IoT, Internet of Things, they are being integrated with distributed energy resources like wind, solar, connectivity of different form. They increase the attack surface. So we need to take into account in a broader context, how do we assess the attack surface? How do we go about reducing the attack surface? So just in a broader sense, not just cyber attack, there could be physical disturbances. There could be combination of physical disturbances and cyber attack that could happen. So one needs to have a solution that takes care of all the situations. There are incidents we know recent years, Hurricane Maria and other blackouts that have happened. Then you have major cyber events like Ukrainian cyber attack, 2015, 2016, Stuxnet. These are all major attacks that were widely reported. There are many other attempts, many other minor incidents that have happened over the year. So just to give an idea, in the Ukrainian attack 2015, it was a coordinated cyber attack targeting 3 distribution companies in the region that is shown in the map there. About 30 substations were targeted. They were isolated. The breakers in those substations were tripped to cause close to 225,000 customers experiencing outage for more than about 9 hours or so. There were various things that were leveraged as part of this attack. I will show you in the next slide. But it is one of the first major attacks that really created a blackout. So what actually happened, the idea here is it's not just information technology, but it's information technology plus OT, operation technology that controls the grid and other physical machinery. There is an entry point through the IT network. From there, they moved on to the OT systems. From that OT system, they were able to manipulate specific controls to cause a blackout. And also they created some sort of collateral impacts, like to slow down the restoration process. They disabled servers, disabled other kind of backup servers and other things. So the idea here is, as I mentioned, phishing, email phishing type of thing is the most common, exploiting the vulnerability in the human in the overall security chain. So there was a phishing attack that through that they harvested the credential, VPN credential. Happens to be this engineer sitting in the corporate network, trying to monitor things remotely once in a while. That connectivity was harvested through a phishing email, that there was a malware downloaded. Then based on that, they were able to gain access into the control center, hijack the HMI, install the malware, remove HMI. Then they were able to trip all the relays in a substation 1, substation 2, substation 2, 3, and so on. Multiple substations like this within the same control center. Similarly, multiple such attacks happened. That's what led to major blackout. So the idea there is the human was the weakest link. Then subsequently, the IT infrastructure, the corporate network, which is connected to the internet, that was exploited. From corporate network to the OT network, the SCADA network, that was exploited because they had the connectivity. Then they were able to hijack the HMI. Then just like the operator sitting inside the control center, the adversary was able to perform those tripping actions in all those breakers. That's what happened. So let me just move on to look at what is the cybersecurity solution itself. So before getting into cybersecurity solutions, we need to understand when we think about cyber physical system, it's not just IT security straight away it is going to be applicable. Probably some cases it is, but some cases we need to understand the sort of the interaction between the cyber and physical system. So typically from the attacker perspective, there are various types of attack as we talked about, malware, phishing, data integrity, timing, and other kind of attacks. They are typically targeted on devices that are there in the grid infrastructure or any physical infrastructure for that matter. It could be relays or IEDs or energy management system inside the control center, things like that. Or it could target the protocols in the system, routers and other protocols attached. So any of these attacks, they target the cyber elements that are part of the grid infrastructure. These cyber elements, just compromising them just by manipulating may not necessarily create a major impact. So one has to kind of go and manipulate the specific control algorithms or influence the control algorithms to malfunction. That is what has to happen. So there is an element, something called control, that lies in between the cyber physical that has to be manipulated. When I say control, that means closing the loop in a feedback control system or automated protection and other type of control functions. So one example is like automatic generation control. We will discuss that is part of the generation. Similarly, transmission side, you have state estimation and other kind of control. Similarly, on the distribution side, any of these control algorithms, broadly, they could be manipulated to create physical impact on the grid, like blackout or violation of stability margin or frequency oscillation, or impacting the market functions and so on. So the idea is, how do we sort of prevent the attacker gaining access into the cyber layer itself? That means you need to have secure servers, secure protocols, secure devices, and so on. Then you need to also have security at the control layer, the substation automation system that is running. You should have capability to detect bad commands or malicious traffic that is coming in. Similarly, the control center should have ability to detect, the control center application should be able to detect bad data, and also able to sort of detect anomalies of different kind. So you need to have security built, not just at the IT layer, the cyber thing, whatever we conventionally know, but they need to also be in the control systems or the specific device software and other things that manages this whole infrastructure. They have to be secure. They have to be secure as well. So the idea is you need to have a defense in depth kind of security, so that these systems are protected against those attacks. So that's what illustrated through this. Yes, smart grid cybersecurity is basically a union of information security, infrastructure security, control system security, that application security, and also physical security is equally important. So that is where in the conventional information security, we are all familiar with it, all those CAA properties, extended CAA properties. Those are all well known, and those protocols or those solution, encryption, digital signature, those things could be properly applicable. Not every context, but some cases, maybe high-end system, they can use those heavy-duty algorithms. But for low-end systems, some of them may be very expensive. One has to sort of develop lightweight or other kind of solutions to take care of such situation. So information security is definitely applicable, not in every situation, to some extent. Similarly, infrastructure security is applicable, like securing the routers and other infrastructure elements, protocols, and so on. Then I talked about the control system, the one about the substation control or the generation, the control center application. All those things have to be secured as well. So the idea is we need to sort of have a combination of these things to have a defense in depth solution. Simply saying no, cybersecurity is taken care by Windows operating system or Cisco router, that is not good enough. We need to also secure the control software that manages the grid, that is from GE, General Electric energy management system. It has to have security inbuilt into those EMS systems. or the SCADA system they produce, or the substation automation system they produce. So that is the focus of this control system security or CPS security research. A lot of people working on for so many years nowadays. But it doesn't mean that the other IT security or the traditional cyber security is not relevant. They are relevant, but they are inadequate. We need to look at defense in depth. That's why it is a union of information security, infrastructure security, control system security, and also physical security that is important. So just to give another viewpoint from a cybersecurity point of view, you may have seen similar diagrams from NIST and other places. Cybersecurity life cycle model, it's not just about the technology alone. It is technology, process, people, regulation. All those things have to be in place so that one can have a sort of comprehensive cybersecurity ecosystem. The first thing is deterrence. Deterrence is not a technology solution, it's more policy oriented. Then prevention, there are a lot of techniques one can have for prevention. Then you have detection, because every attack cannot be preventable. Then once you have detection, how do we mitigate? The mitigation could be, that is where when you say detection and mitigation, they could be model-based mitigation or machine learning-based mitigation, similarly for detection and so on. Then you need to also have resilience. That means if some events happen, there is an impact, but we need to maintain the minimal operational state for the grid without causing major blackout. So resilience is an important consideration when it comes to cyber physical system, especially critical infrastructures. Then attack attribution, that is about more of a forensic study to make sure that who did it, or even if you have that capability, people may hesitate even to undertake any attack. Attribution itself serves as a deterrence. So in this wheel, what you see is as a life cycle model. There are a lot of research challenges are there, like risk assessment, risk mitigation. How do you reduce the attack surface, like moving target defense? Those kind of solutions we have worked on. There are other kind of things, prevention techniques that you can have in this context. But we need to make sure that these things don't incur too much overhead in terms of computational overhead and communication overhead, so that they are feasible, they are deployable within the limited, within the timing constraints and other properties of this cyber physical system. So that's again, when we come to intrusion or anomaly detection, there are model-based, machine learning-based. Similarly, for the mitigation, model-based, machine learning-based, those things exist. Then the resiliency, again, it comes to cyber physical resiliency. How do you manage the system? What kind of strategies you have in the physical system reconfiguration or cyber system reconfiguration? So a lot of mathematical tools like machine learning, game theory, those are all very valuable, not broadly in different contexts. Similarly, there are several enabling technology like synchrophasers, like PMUs, and other technologies. They are very useful. Software-defined networking, another important technology for dynamically configuring the cyber network that is being widely, actively researched in recent years to look for bring some kind of dynamism into the infrastructure so that the adversary doesn't have advantage. So there are a lot of research opportunities exist, and many researchers, including Iowa State and many other researchers, national labs, DOE national labs, they are pursuing this area very actively. So this is just to give you an idea. Let me look at the time. So this is the DOE, they have signed a map to map which projects falls where and so on. Most of our research falls into the bulk power system, cybersecurity, in the wide area network point of view, energy management system point of view, substation automation point of view. Those are the things we focus. We haven't done much work on the substation, the metering or those kind of work, but more on the bulk power system, substation, control center, and also wide area communication network. So just to give you a couple of case studies about cyber security, CPS security kind of research for wide area monitoring, protection, and control. Wide area monitoring and protection control is the backbone of the bulk power system. That is the brain of the bulk power system. If there is any major event, in those or manipulation in those system, they will have major consequence in terms of grid stability and uh, uh, meeting performance requirements and reliability and so on. So that's why protecting the bulk power system means we need to protect this WAMPAC or wide area monitoring protection control application. So this is what the snapshot of WAMPAC. You have a power system, various sensors are there. There is a transmission network. That is where the various measurements are coming over the wide area network. They go to the control center. The control center has energy management system and other kind of thing. It could be protection, it could be control, it could be monitoring kind of application. This suite of analytics that is happening as part of the energy management system. They rely on measurements that are coming from the field. They make intelligent decision. They close the loop, control the system back. So this whole feedback control loop, it happens different time scale depending upon the application. Some are happening in seconds, some are happening in several minutes, some are happening several tens of minutes, and so on. There are applications that are happening locally, like some protection application and other things, in milliseconds. They don't necessarily go to the control center and get the decision done, but they are locally done. They are very sensitive to timing. So you see the moment wide area communication involved, they are susceptible to cyber attack. In terms of solutions, when we say attack resilient control, there are model-based solutions exist, rule-based solution exist, or machine learning-based solutions exist. So a lot of those things, what we try to capture in our research, attack resilient control system is basically anomaly detection plus attack mitigation. So having this capability online, ability to detect attacks in a cyber physical sense, and also ability to mitigate, we call it attack resilient control system. This all this EMS application, what I mentioned, that are running here, they have to be protected or they have to be enhanced with this attack resilience capability, so that even if any of those measurements they are corrupted, they are not affected. They have the ability to detect those attacks and the ability to correct from it. So that's the whole idea. So let me just give you one example, the automatic generation control, which is the wide area control application. For that, before going there, this is a simplistic view about cyber physical system. So you have a physical system, various sensors are there, you take the measurements, then those measurements go through the wide area communication network, it goes to the control center or some level of decision logic. That is where the decision is made, various kinds of application as I mentioned. Then the control comes back to actuate the physical system. This is the typical feedback control loop. As I said, there are several feedback control loops exist. Some are at the seconds level, some are milliseconds, some are at minutes, and so on. Some are supervisory control. That means the operator looks at it. It's not automated control. Supervisory control exists, automated control exists. All these kind of application, they are going through wide area communication. They are susceptible to attack, both the sensing side, also the control side. We need to make sure that these attacks don't happen. Of course, the attacks could happen on the sensors themselves. That is also possible. So the typical attacks, data integrity attack, denial of service attack, timing attacks, different types of attacks are there. Even if the channel is encrypted, one can create a timing attack or denial of service attack. We need to sort of protect the system against those attacks as well. So this is the automatic generation control. As I mentioned, it is one of the critical control system application at the control center, EMS application. So what it does is it basically maintains the system frequency at 60 Hertz in North America. The idea is to sort of match the supply and demand. If they are balanced, the frequency stays at 60 Hertz. You see the scale here. What you see is if they are balanced, supply and demand, they are balanced, it stays at 60 Hertz. On the other hand, if you generate more, the supply is more than the demand, then the frequency shifts towards the positive side, 60 plus some delta. So that is not good. You need to bring back, in that case, you basically ramp down the generation. You don't need to produce that much. So that is the control action needs to be done. On the other hand, if the demand is low, like what happened in Texas a few weeks ago, the demand was so much, there was not enough supply. Some of the generators they couldn't produce, generate because they were frozen and so on. In those situations, what happened? The frequency starts sort of shifting towards the downside. That means you have under frequency. So if under frequency happens, that is also not good situation. The relays and those protection devices, they are under frequency protection or over frequency protection. There is a guard band. If the moment it goes out of the guard band, then these relays will trip to prevent faults in the system. So the idea of frequency control is to make sure the demand and supply, they are managed, the ramping up or ramping down generation so that the frequency stays at 60 Hertz. And also AGC is very important from the economic operation perspective. Among the generation, which generation has to be ramped up, ramped down, that also the decision has to be made based on economic reason, not just random generator. You want to use the least expensive generator to ramp up. So economic operation is the secondary goal for AGC. Primary goal is to keep the frequency at 60 Hertz by matching the demand and supply. So that is what happens. So it is a very important application. And in the North American grid, US grid, as you see, there are balancing authorities. There are 100 plus 106 or so balancing authority. Those white nodes kind of thing, those are balancing authorities. They talk to each other. As we notice here, the Texas, we all read about it, ERCOT, that is the balancing authority. There is nothing else. So they also have very limited, it's a grid by itself. It has some connectivity to the tie line, to the neighboring grid, but not whole lot. Whereas the rest of the grid, you have Eastern grid and Western grid, WEC, you have so much connectivity to share power and so on. So the tie lines are important. So the tie line basically allows our neighbors, they talk to each other like a service level agreement. In a communication networks, you have a SLA, same way buy and sell energy between neighbors, that is done through your tie line. So the idea here is you have AGC algorithm that is running inside each one of those balancing authority. Balancing authority is responsible to keep this frequency at 60 Hertz. Each balancing authority does that way, and they coordinate among themselves in an overall way so that the entire grid is operated at 60 Hertz. So the AGC algorithm running at the control center relies on two critical measurements. Going back to the control system diagram I showed, the measurements are coming from the field. One is the tie line flow measurement. The other is frequency measurement. What is the current frequency? Based on that, this is the ACE, which is area control error. That is what computed, which is delta P net plus beta times delta F. What is delta P? Delta P is nothing but what is the scheduled flow to your neighbor as part of the service level agreement. How much buying and selling, the scheduled flow, what is the actual flow that is going on, the change, the difference. Similarly, what is the delta F? What is the frequency? 60 Hertz, that is what desired, but what is the actual measured frequency? So this difference is delta F. Obviously, if ACE, area control error, if it is equal to 0, then currently the supply and demand, they matches. The frequency 60 Hertz, we don't need to do anything. The ACE is 0, don't need to ramp up or ramp down any of those generation, things are fine. This feedback control loop, sensing, decision making, closing the loop, it is automated feedback control loop, and it takes it happens every 4 seconds in the grid, in the wide area grid for that particular balancing attack. On the other hand, let's say currently the frequency is at a low, measured frequency is low, which means there is definitely the load is high. If you see back, frequency is low means load is high, demand is high. So then this positive ACE value indicates some of the generation has to be ramped up. And the generators know they have some kind of participation factor, how much they are willing to participate, how much cost involved, and so on. Based on economic operation and participation factor, the AGC algorithm will instruct a group of generators to ramp up certain amount. That's how it will basically ramp up to increase the frequency to sort of bring this A's to 0. So this process continuously happens every 4 seconds. So what is the cyber attack here? The cyber attack here is the tie line flow and the frequency measurement that are coming over the wide area communication network can be systematically manipulated by the adversary so that to fool the AGC algorithm to wrongly ramp up or ramp down, causing further oscillation in the frequency. That means it's an automated control loop. The algorithm is utilizing or using the wrong information. Based on that, it calculates the A's value, which is erroneous. That erroneous A's value causes unnecessary ramp up or unnecessary ramp down, causing further degradation in the frequency. That's what they do. So modify the tie line and frequency measurement, abnormal operating frequency conditions, and also uneconomic generation. So economic sense, it can have impact as well. So for example, we have studied several attacks in this context. It could be a scaling attack, ramp attack, replay attack on the wide area channels by manipulating those measurements. So what you see is the actual load in the solid line. Actual load is this, but the measurements can sort of change to cause the perceived load to be somewhat different than the actual. If the perceived load is higher than the actual load, what happens? Oh, load is so much, so we need to increase the generation. So for this one, the action will be ramp up. Ramp up means it will unnecessarily increase the frequency beyond what is needed. So this is the attack impact on the system frequency. What you see here is if there was no attack, the middle case, so the solid line, you have everything is at 60 hertz, nicely maintained. But due to any one of those attacks, scaling attack or ramp attack or pulse, the third attack, replay attack, any one of them, the perceived load to be different from the actual load. In this case, the perceived load was to be higher than the actual, so the generators were forced to ramp up. When you ramp up, when it is not needed, the frequency shoots up, goes up above 60 hertz. When it goes up, those over frequency relays will trip, and it will have secondary effects and so on. So these are the kind of things that can happen. There are several studies like this. Those are published in our papers. But one can create, stealthy attack on wide area control loop like AGC algorithm to create further degradation in frequency rather than stabilizing the frequency. That can happen. So how do we mitigate this kind of problem in the system? How does the energy management system, the control center application, can detect such anomalies and mitigate those anomalies? So one example is, can we rely on some information other than these measurements that are coming in so that we can validate? That's where the notion of model-based mitigation or model-based detection and mitigation come into play. So one can rely on what are the sources of data that can be useful. One could be load forecast, because supply and demand, that is what the frequency depends on. Here, okay, what is the load? Not the exact load, but one can have a pretty good estimate of what is the load forecast. These are broadly done unless there is a major fault happens. Otherwise, load forecasts are pretty accurate. So that data is usually available. One can take that load forecast data, real-time load forecast data, and that load forecast data, and there are other things like system data, like what is the generator inertia and other kind of properties. You can use those things. So this is the model-based anomaly detection and mitigation kind of methodology. I'm not going into the detail of specific implementation, but what it does is, you have, let's say you have this AGC algorithm relies on the measurements, actual measurements that are coming in the field. Those based on that we computed the real A's value that is computed, but we don't know this A's value is erroneous or accurate. But we want to do some kind of validation check on this A's value. For validation purpose, we are passing this A's value through an anomaly detection engine. The anomaly detection engine relies on model of the system. For model purpose, we use the load forecast, real-time load forecast. Based on the real-time load forecast, a forecasted ACE is calculated. It's not exact, but forecasted, but it is error-free from a attack or other kind of faults or anything, that it is error-free. So you take ACE forecasted, ACE real, then you do some kind of statistical test, whether it is within 1 sigma or 2 sigma, whatever the bound that is acceptable. Just to check if statistically it is within that allowable bound, yes, this passes. It is not too much deviation, is perfectly fine. That is one. The second one is rate of change. First one is the statistical characterization of ACE. The second one is the temporal characterization. What is the rate of change, the ACE value? What is the previous ACE value? What is the current ACE value? What is the next ACE value? Rate of change of the ACE value, is it complies? Does it comply with what is expected from the model as opposed to what is actually happened? Because this physical machinery, you can't go and change, ramp up, ramp down, all those things so rapidly. Generator cannot ramp up, ramp down instantaneously. They have inertia. It takes some time to go up and down. Based on that, the actual ACE value would be different. So the rate of change essentially captures the machine, the generator and other parameters inherently, whether the actual ACE that is calculated is consistent with that. Otherwise, if the random attacker, they just randomly go and change the measurements, those things will be caught. Okay, you can't go and arbitrarily change the tie line frequency, tie line flow measurement, frequency measurement. They are not consistent with the physical property of the machinery that controls this generation. So temporal characterization can catch those kind of properties. So you have a statistical characterization of ACE and temporal characterization. If these two tests are, let's say, it passes, then there is no anomaly. So then you can use the the actual value, the real value, real ACE value. There is no anomaly. We can use it for controlling the system, ramp up or ramp down. On the other hand, if there was an anomaly detected, then it will be resort to forecasted ACE value based on which ramp up or ramp down that will be done. It's not accurate, but it's better than operating the grid based on manipulated data. It is approximate model-based mitigation. So this is the sort of broad framework wherein you can use a real-time load forecast for anomaly detection purpose, and based on the model value, you can make the decision to ramp up or ramp down. This framework broadly applicable to many other wide area control and wide area monitoring applications. So that is one example. So the results just to show what it here it shows. When you have a scaling attack, in that case I showed you before, the frequency was going up without mitigation. That's what was going up. With the mitigation, the model-based mitigation, what I showed before, the frequency is pretty much stays close to 60 Hz. Not exact, because it is not based on the actual measurement. Instead, it is based on the model forecasted load forecast model parameters. It's still within the acceptable guard band of the frequency. That's what shows. So it's basically, there are several studies like that for ramp attack, scaling attack, replay attack. In all those cases, the model-based attack detection and mitigation algorithm is able to keep frequency close to 60 Hz. So let me go to the second case study. In the interest of time, I will quickly rush through. This is about wide area protection. This is where machine learning we have used, and this work was done by my recent PhD graduate, Dr. Vivek Singh. He is currently at Idaho National Laboratory. I believe Vivek is also on this seminar session right now. So what is the wide area protection? This is also relying on wide area measurements. It's an automatic protection system to designed to detect abnormal or predetermined system conditions and take corrective actions to sort of stabilize the system, not to allow the fault to propagate, and so on. So there are the RAS, remedial action scheme, very powerful one, very critical system wherever critical generation and the critical part of the grid is there, the RAS is on. You can arm the grid. Then when it is triggered, when it is actually fault happen, it detects. It does various things, generation drop, load shedding, or other things to sort of clear the fault and stabilize the grid. That's what it does. So many times what happens, there is something called RAS controller, which coordinates between multiple relays. These relays, they have a coordination with the RAS controller. They report what is being detected. The RAS controller makes some decision, then it responds. That's how this whole RAS scheme works. So they are the RAS controller itself could be centralized or distributed or decentralized. So decentralized means they are very fast response, like 100 milliseconds. Those kind of things, it has to be decentralized right at the substation level. The substations, nearby substation, they coordinate relay in one substation, coordinating with relay in another substation through a RAS controller. They just mitigate the situation right at the local level. Those are fast response, like in 100 milliseconds or even less than 100 millisecond kind of application. There are other kind of applications, centralized, that means they are at the control center. That means all these measurements, they go to the control center, and the control center makes decision to protection type of decision. So those are like, in terms of seconds, not milliseconds. Those are very much possible. Then a lot of major companies, Southern California Edison, BPA, Idaho Power, BC Hydro, many companies, they have RAS scheme implemented in critical parts of the grid. So it's a very important application. So this, it could, again, conceptual diagram, you have power system, relays, these measurements are there, the RAS controller, whether at the local level or at the control center level, if it relies on some malicious data, it can take wrong action and it can result some attack. I mean, system, what you call undesirable situation like blackout. This is just to illustrate a 9-bus system. Let us say there is a RAS controller which coordinates this portion of the grid, for example. Let us say there is a malicious trip attack that happened. It can very well, it's very much possible to make it happen. This relay is tripped, this RAS controller recognizes, then what it does is, typically the normal operation is, okay, this relay is tripped means this particular line is out. Then it will instruct the this generator to ramp down, because if one of the line is out, you ramp down so that only this, whatever capacity of this line, only that much generation has to happen. That is what the action in response to outage or line tripping due to fault or due to cyber attack, doesn't really matter. The RAS controller recognizes that and inform the generation controller for G2 to ramp down. That's what happens. So a orchestrated stealthy attacker would do trip attack here, then do a DOS attack on this RAS controller or the communication network associated with the RAS controller to ensure the command, ramp down command, never reaches the generation controller. When the ramp down doesn't reach here, the G2 doesn't know. It continues to send at the same, generate at the same level, causing this particular line to have experience thermal overload. When you send them at more energy is pushed over the conductor beyond a limit, over the limit, then there will be a thermal overload. Relay R2 will trip automatically because it will detect thermal overload. There is something is wrong, it will trip. So basically what happened, just creating a cyber attack that involved a trip followed by a DOS attack resulted in a cascading effect of R2 tripping by itself. That causes this whole thing, B7, bus B7, B2 and G2, this whole thing islanded from the rest of the grid. So the rest of the grid, that much G2 generation is not available, that much load shedding has to happen. This is a simple illustration to show how important this RAS and this very sensitive application. So Vivek work focused on protecting or detecting this kind of attacks on the RAS controller and mitigating those attacks. So since it is a little close to 11:50, what I'm going to do is we are going to look at, just to give you a snapshot, looking at cyber attacks and also physical disturbances, both are taken into account. Cyber physical kind of anomalies that are happening, and they are basically going to be classified one way or other. For that, we are basically using machine learning. The machine learning algorithm relies on data about the cyber layer, about the physical PMU based measurements from the local PMUs, from other PMUs, and also the cyber log data, like what is a let's say if there is a device attack, the packets don't come at regular interval, there is a delay, the inter arrival time between packets, the spacing, the size of the packet, those are the cyber log. Then the PMU, the voltage, the phase angle, magnitude, rate of change, those are all derived features. Those are all used to train the machine learning model. He uses what is known as variation mode decomposition methods to classify the signal into high frequency, low frequency, and depending upon the attack. Then based on that, this the different detectors, model 1, model 2, there are variations of the model. At the end, this model will classify the events to be single attack or coordinated attack or line faults, like fault event, disturbance happen, or normal event. For this to occur, one needs to train this model for a large number of cases, like normal cases, fault cases, single attack cases, multiple attack cases, and also fault and attack together. All those cases he has studied for thousands of, or close to 880 cases, like line fault, right? Line to ground, line to ground, and so on. Similarly, cyber attack, malicious scripting, pulse, ramp, denial of service, those attacks. Then you have a coordinated attacks, that means multiple events happening simultaneously. All those events, physical disturbance, attack events, and the combination of this, they are part of the training set to train the model. Then once you train this model, using this model, you can sort of this VMD based thing with decision tree. That is what he is using. He is using decision tree to classify whether it is one type or it's a multi-level decision tree algorithm. At the end, it will basically classify this to be attack, or it is a normal event, or it is basically a fault event. That's what he has classified. And this is basically implemented in the Power Cyber testbed at Iowa State. It is a hardware in the loop testbed with OPLRT and PMUs and relays and other devices that are incorporated. This, by the way, this work somewhere, yeah, it is also just recently got accepted at IEEE Transactional Smart Grid. All those details are presented there. So what he has found, the VMT, variable mode decomposition technique, with various machine learning algorithms, KNN, decision tree, and so on, he found that the decision tree based algorithm achieved the best performance in terms of detection accuracy. Those are all summarized here. And the processing overhead, because these are real-time application, they are sensitive to time. Their timing is very, very within the margin, like 2.6 milliseconds it takes for the centralized VAS scheme to work, but it is within, very much within that 200 to 300 milliseconds that is required for this such a RAS scheme to work, especially the Southern California edition. Their implementation requires the 300 millisecond round trip latency. This 2.6 millisecond computational overhead is well within that budget. In the case of decision tree based classification algorithm that he has. Then subsequently, he also implemented rule-based mitigation. It's not machine learning-based mitigation. It's a rule-based mitigation based on the state, whether it is a normal state, pre-alert state, alert state, or it is in compromise or critical state. Different decisions, what needs to be done. Some are at the cyber layer, some are at the physical layer, some are at the cyber and physical layer. Like, for example, you can do a cyber islanding, or you can restore line, or you reroute the flows and things like that. He has a comprehensive set of rule base. Based on that, those mitigations were activated.
So Manimaran, I'm so sorry. We are a little bit going over time. So this is very exciting. We would like to leave maybe just a minute for maybe one question at this time.
Yeah, yeah, I'm pretty much done. Yeah, this is the last slide.
Awesome, awesome.
Yeah,
I'll
but
just
I was able to say we have a test bed, and yeah, I mean the test bed, that's where we evaluate all those things, and it's a hardware in the loop test bed. We do vulnerability assessment, risk assessment, risk mitigation, attack defense evaluation, and also demonstrating real use cases like Ukrainian attack and its countermeasures. All those things are implemented in our test bed, and this is my last slide conclusion. So CPS security is very important. There is a lot of R&D that still needs to be done, and there is a lot of collaboration opportunities do exist in this area. And I would like to thank all of you for listening, and also our sponsors for these projects, and many of my collaborators, including Vivek and many of my former students, to help me in this research, and many other collaborators along the way. Thank you.
Thank you very much, Manimaran. I will mention that Dr. Govindarasu was elevated to a fellow IEEE in 2015 for contributions to security of power grids, and Dr. Govindarasu is highly cited, the H-index 42, with over 8,500 citations on the topic of security of SCADA and CPS systems. We are unfortunately out of time. Maybe we can afford just one quick question if anyone would like to go ahead. If not, Manimaran, I will ask you for just quick reflection on, since a number of us are working in the data science, AI, machine learning angle applied to various topics, including but not limited to cybersecurity. Could you give us a quick reflection on how do you see machine learning when it comes to this context of CPS?
That's what it is, because there's a murder out there.
The Cronin.
Yeah, thank you for that question. I think it is a rich area of research. There is so much potential exists. The key challenge there is the availability of real data sets to really understand what is this data set represents, whether those suitable speeches that we take it, extract from those data sets to build those models. So I would say a lot of, especially in the cybersecurity area, CPS security area, wide area monitoring, protection, control, all those application areas that rely on measurements or data, both from the cyber world and physical. How do we sort of fuse both type of data, cyber physical data, so that now you have robust machine learning model based on which you doing anomaly detection or mitigation, those kind of thing. That is a fertile area of research, and it has a lot of promise in securing the infrastructure against most stealthy and a lot of unknown what you call zero-day exploits and things like that. So as you mentioned, alluded in your question, it is an area that a lot of researchers have started working on it, but the critical aspect is having reliable data sets, so that these models and all kinds of scenarios, one can study these things and validate those models. Very important. Otherwise, we have some data sets where for that it works, some other case it doesn't work. So having a benchmark data set also will really help. But these are all ongoing work. I'm sure down the road, those kind of benchmark will be available. Like, IEEE power system model of this kind. Data sets are available, synthetic power system model. Same way, one has to have data sets for the grid of different kind. But especially when it comes to cyber attacks, there is not a whole lot of data sets available. You can get PME measurements and other things for events, fault events, normal events, and so on. But for fault events, they are rare. So for cybersecurity events, they are rare. So it's a kind of challenge. Actual data combination with the synthetic data could still go a long way, but the data is very critical, and it's an area that definitely has a lot of potential, and many researchers have started working on.
Well, with that, now we'll regretfully have to end. Thank you very much for your great presentation, and we look forward to talking more on these topics. Thank you again, and have a great weekend, everybody.
Thank you very much. Have a great weekend.
Thank you.
Bye.
Thank you.
Thank you.